Michelle's not here. Is she? No? Good evening, everybody. Welcome to University of Canberra. It's a celebration tonight. But before I go any further, I'd like to acknowledge that this is Ngunnawal country. This country has been cared for thousands and thousands of years, and we pay our respects to the elders of the Ngunnawal Nation and any Aboriginal and Torres Strait Islander peoples here today. And I would recommend that you grab your coat and you grab your beanie and you get to know this country. I recommend that, now it's a little bit drier, you walk out to Tidbinbilla, or you take the car to Tidbinbilla, and then you walk to Yankee Hat and go and see the rock paintings. I recommend that you walk up Mount Majura and you look for stone tools, and that you get to know the country. Find the scar tree on Mount Painter. Hands up if you've found the scar tree on Mount Painter. Hands up if you've walked Mount Painter. You've all walked Mount Painter and you haven't seen the scar tree. Get to know your country, get to know this wonderful country, and get to learn the history of the country and the way it's been cared for thousands of years. So welcome to, well, acknowledging that this is an Ngunnawal country. Thank you. Now, celebration tonight. Very pleased to be celebrating Ben's first professorial lecture as a professor. Yes, you can clap. Huge accomplishment and the pinnacle of an academic career to be appointed as professor. So, and for those who don't know me, because I forgot to say at the beginning, Jenny Scarville, Associate Dean of Research, Faculty of Health, and welcome all of you to University of Canberra. I will hand over now to Professor David Pine, who is the Director of the Research Institute for Sport and Exercise, and he will introduce Ben properly. Thank you.
Thanks very much, Jenny, and let me add my welcome to all the distinguished guests, students and members of staff here at the University. We do have a small selection of international guests, but most importantly we've got Ben's immediate family here, so I know that means a lot to Ben. And this really is quite a prestigious occasion to acknowledge the fine work, the contributions of Ben and his promotion, which did happen several months ago. So he's the final in our series of professorial lectures. So that's a long-standing tradition in the University and in the Faculty of Health to provide the opportunity to introduce either new faculty members, incoming professors, or even perhaps more importantly, it's those hard-working members of staff who've achieved success in promotion. And so we run those 4 or 5 times a year, and it's great to see here now so many people in a face-to-face environment. So welcome. And I hope you enjoy this session as much as we will in hearing from Ben. So I've known Ben for 15 years through his academic career, and he's very well established and has a fine reputation here at the University, in the Faculty of Health, particularly in his fields of endeavour, so his lecturing and his research work. So Bell is a highly recognised and a highly valued member of staff. He occupies an important position not only in terms of his teaching and his research, but also his academic service and contributions. So the promotion process, Ben, as you will no doubt recall, involved really identifying those contributions he's made over those 15 years. And really I think that's the depth and the breadth of those contributions. And he really has contributed at the university level by way of committee membership at the highest level, and in terms of dealing with the Faculty of Health here and the discipline of sport and exercise science, and it's good to see so many members here. and his current group of students. Welcome one and all. Ben's area in more recent times has been in the area of the active brain and neuroscience, and doing some quite world-leading work in that area around the connections between lifestyle, exercise and the brain. So this whole area around cognitive control and cognitive performance. So coming from your own experience as an orienteer and a very well-credentialed athlete in his day, and then through his academic teachings and his research. So Ben is now positioned as a world leader in this area of active brain research, and you collaborate with the world leaders here at the ANU in Canberra with Professor Nick Cherbuin and esteemed world-leading experts, Professor Romain Musin from Belgium. So your reach is far and wide, Ben, and we're very honoured to hear from you today. So would you please welcome Professor Ben Rattray.
Thanks, David. That's very kind. Didn't expect all of that. Of course, the very first publication that I had was with Professor Pine as well, many years ago. So, yeah, we have a long history going back. So, when you get asked to do a professorial lecture, it's your first one, right? You don't really know what to do. So, I've got a little bit of a mix in here. So, I hope it's something for a little bit of everyone. Both obviously about the research work that we do, the research work that I hope we will do, and also I took the opportunity, of course, to talk about myself a fair bit as well. But I'm going to start somewhere a little bit different, and I'm going to start by talking about sea squirts. I've just got to make sure I turn the sound off because it's really dominating. So sea squirts are these animals here, right? They essentially look like a sponge. Some people mistake them for coral. They are a filter feeder. So essentially they push water in the sea through themselves, and they filter the nutrients and stuff out. But they're not a plant, they're an animal, because they have this thing called a notochord that you can see on the screen. The notochord is what we have too when we're in our very early embryonic stages, because it is the precursor to the vertebrae. So it's our spinal cord, but it's a very early version of that. Now, for sea squirts, or tunicates is the scientific name, they actually start off as an egg. The eggs get laid, and then for the first perhaps 1 day, or perhaps it's up to about 5 days, they actually look like a little tadpole. And they swim to the site that they will live the rest of their lives. Now, the fact that they swim there tells you that they move, they find a place that they're going to live on, and that might be on a jetty pylon, on the bottom of a boat, or on the bottom of a sea floor. And what's really interesting at that point, though, is once they finish moving to where they're going to live for the rest of their lives, they essentially consume that notochord. In other words, the only brain that they have, they then eat once they don't need to move anymore. So it's really interesting, right? Evolutionary biologists believe that is part of the evidence that goes towards what the brain is for, or what the neural system is for. And originally, it is very heavily about movement. Now, in humans, of course, we have a much more complicated nervous system or brain structure than the actual sea squirt that you can see up here. And most people think about movement coming from a particular part of our brain. So those people that know a bit about the brain will often associate movement coming from this motor cortex. There's this band of nerves that kind of come from ear to ear over the top. And that controls a lot of the movement we do. Or at least that's how we think about it early on. But of course, it's much more complicated than that. This is a model of a macaque brain, so a primate brain. Not quite as complicated as ours, certainly much more complicated than a sea squirt. And in this diagram, essentially what I want you to take from this is how people think the brain is working when a monkey, the macaque, technically not a monkey, I believe, not a biologist, but a macaque is tracking an object and moving, say, the hand to a position that they can grab that particular thing. And the point really is that the whole brain is involved. There's the sections at the back of the brain that are processing the things that you see. They're informing parts in the more frontal areas of the brain that are making decisions about, is it even worth it? Like, is it going to be tasty or does it not look good? Is it worth this effort to grab? And then there are many other parts of the brain that are refining the movements, taking on feedback, and allowing us to move in the very intricate ways that enable us and, of course, the macaque. So evolutionary biologists will argue to you that because of our very long history or evolution as a hunter-gatherer lifestyle, if you just look at the picture on the left for the moment, then our brain is basically made to move. Every single part of movement and the brain are designed to work together, and both from an acute sense, so those boxes in the middle, where movement basically enhances the way our brain works, our brain in turn enhances the way that we're able to move. And then, of course, if you do that over and over time, as we do, then you get long-term adaptations as well. And so the evolutionary biologists will argue very much that physical activity is not only crucial for the brain, it is the brain. It is what the brain is was originally designed to do. Now, of course, I have a massive cognitive bias towards this because, well, if we just start with my early childhood, I moved a lot. So I like the idea of that argument, right? It supports everything I believe in. So of course I'm going to be heavily biased towards that. I remember my reception teacher or kindergarten teacher, her name was Robin Cutton, Miss Cutton, who I eventually found out was an orienteer later in life, but that's another story, told my parents that all I would do was run all day during kindy. And it turned out that I was a pretty good runner. Eventually, I was fairly successful. I did quite well in terms of cross-country running, track running, endurance running, etc. Joined an athletics club, my local athletics club, in the later years of my schooling. It was Flinders Athletics. Flinders Athletics Club was one of those types of clubs where, you know, I was a good runner, but I was at the back of the field. But of course, there was an Olympian there. There was the Australian track mile record holder there. And then there was someone going off to run the World Cross Country Championships. And it was a very daunting environment. So I very quickly learnt that, okay, I was a good runner, but I was never going to be an Olympian. And so one thing that changed very quickly was I started thinking about how I could use that running. And I very quickly turned my attention to orienteering. And that's not a reflection that orienteering was my second choice. Maybe it would have been if I was a better runner. But I certainly wasn't good enough as a pure runner. So I used that and became quite successful within orienteering fairly early on. Got lots of exposure to things like national training camps. I was a scholarship holder at the South Australian Sports Institute. And I mention that mainly because I was in a sport at that time of orienteering where obviously you run as fast as you can, you're navigating, you have a set course, you're basically trying to interpret cartography, a special cartography map, and make your way around a course. So it's very cognitively engaging. You can see where all this is going to go, right? And I'm running along at the same time, and I spent a lot of time also with people like sports psychologists and stuff. And this is, you know, a fair few years ago when I think even sports psychology was probably not as embraced as it probably should even be right now. I then went on to undergraduate. I'll probably shock a few people right now. My first choice at the University of South Australia was Bachelor of Physiotherapy. I couldn't make the grade, I missed out. I'm super thankful for that, to be honest, right now. I wouldn't have made a good physio, that is for sure. So I studied Bachelor of Sport and Exercise Science. During that time, not only was I an athlete at SASI, but I got to do my work experience, and I did quite a lot of extended work experience at SASI. And that was in particular with a few of the big names that there were back in that area, like Pete Borden and a few others. I was a national squad member for orienteering. I ran World Juniors. I got all sorts of exposure that people don't, not lucky enough, I guess, to embrace. But I'll just point out one thing about orienteering. Obviously, it's going to come up more. I can't help myself. But if you remember back to what that evolutionary model of what the brain is useful for, there is almost an exact duplicate going on in terms of if you think of the skills that are involved in orienteering. And what I mean by that is, you know, it's a aerobic activity. You're running through terrain, uneven terrain, so you need quite a lot of endurance, strength. You need a lot of balance, proprioception, if you like. Clearly, it's wayfinding. That's everything it's about. You have to be very attentive. You're problem solving. There's a lot of planning that happens within an orienteering setting. It is a very hunter-gatherer skill set. I mean, you're not running away from some kind of beast, I guess, but there are other elements that are going on quite a lot. And for those that orienteer, there's a lot of travel often involved and a very social based sport. So in many ways, I think there's many overlaps between the sport of orienteering and what the evolutionary biologists would argue that the brain is for. So I finished my undergrad. I took a gap year at that point. I moved to Melbourne the year after that. I studied at the Victoria University. I did a graduate diploma, again in sport and exercise science. In the year that I was there, I worked at the Victorian Institute of Sport. I did a sports science traineeship that they had there. You can kind of see that I had this aspiration, right, to work as a sports scientist. That's what I was driving myself to do. And I only spent a year in Melbourne, but I trained a lot, like a lot. You know, like athletes do. I came away from Melbourne, and that was the end of 1999, and I was probably as fit as I've ever been. And the result of that was that in 2000, I had a really successful year. Not only was I running World Cups and stuff for orienteering, but I managed to make a Athletics Australia team as well. I ran in the Australian World Mountain Running team. So again, I wasn't an Olympian or anything, but I was a pretty good athlete by that point in time. I had a sports scholarship with the University of Canberra back in the day. I did a Masters in Sports Studies. I did a Masters by Research here at UC. That is the icon that was used back there. That academic hat sitting on the runner thing. It was a while ago, so. I worked at ACTAS, I did some casual work at the RAS. I was very lucky to be in those environments. I came to Canberra not because I wanted to study at UC, no offence, but I came here because they had a national sporting program and a national squad and stuff, and I got to go to the Walk of Fame the other day, and you could hear a few of the people say, "Why did you study at UC?" And they were like, "I came here because I was an athlete and I was trying to get better at my sport." To be honest, it was no different. I was here for that. But that year, in 2000, was also the year that this particular article came out. And so I wanted to put that up because it probably changed completely the trajectory of where I would have gone. Now, I swore, even at this point, I would never do a PhD. Like, being a professor was absolutely not even considered, let alone an aspiration of mine at all. But this particular paper, as you can imagine, right, I'm an orienteer, I'm an athlete, I've done a lot of sports science, and I'm always kind of sitting there questioning, why don't we talk about the brain? Like, there's so much going on in the brain. I'm an orienteer. I run up a hill, and all of a sudden, I'm foggy. I can't think as well anymore, right? So I'm always thinking about, well, what is this link between physical activity and the brain? And no one's really talking about it until Tim Noakes, very controversial South African character in his own right, starts writing these papers. I don't agree with these papers at all. I don't think they're right. But what he did was he changed sports science and how we talked about it. And I remember this paper coming out and sitting around with the other sports scientists at the ACT Academy of Sport, and we just workshopped this article and we talked about it. And from that point on, I think sports science changed and started embracing that there was a link between the brain, I mean obviously, and exercises that we needed to understand. And so from that point on, I think everything happened. And of course, what also happened in my time in Canberra was I had a fairly horrific ankle injury and never really went anywhere with sport after that. So of course, when you're not an athlete anymore, you go to the UK. I lived in Glasgow. They drank a lot, like a lot. But I was fortunate enough to work at the University of Strathclyde in Glasgow, was the place where it was involved, and I worked with Scottish Institute of Sport, West of Scotland Institute of Sport, Glasgow School of Sport, British Swimming. I worked with a number of partners. I was basically effectively a consultant to a whole bunch of things. I worked mainly with swimming, badminton. It was a very steep learning curve about badminton. And I did a whole bunch of other sports, including athletics and some snow sports and obviously some fun other things. And I embraced British orienteering while I was on there, and I went on quite a few training camps for them. And you know, they were people that would just take a squad of 50 athletes to Sweden for 2 weeks and pay for everything and stuff. It was just crazy in that time. But I learnt a lot. And I think a lot of this background that I'm trying to present to you is I think, for me, it's important because it shows the variety of influences that I've had. And I think, and even what I will say to any student now, try to expose yourself to as many environments as you can and learnings as you can, because I think, to be honest, I think that's my main strength, is that I have worked and been exposed to, in different ways, I guess, a whole bunch of different environments. So I worked in the UK for a few years. I came back to Australia, couldn't get a job, couldn't get an interview, to be honest, even though I'd worked in the industry for so long. Everyone goes, "You don't have a PhD, Ben." I'm like, "What?" And then all of a sudden, where did I find myself? I found myself enrolled in a PhD. I remember talking with my supervisor, the now late Martin Thompson, and I wanted to, of course I was a naive student, right, trying to basically win a Nobel Prize at the start of a PhD. And I remember it was about, I wanted to understand better the role of the brain in performance. And the next thing I knew, I was measuring calcium fluxes in the skeletal muscle mitochondria of rats. I still don't understand how that happened. So I was a biochemist for 3 years as part of my PhD, and it's a skill set and everything that I really loved, but never really got to where I wanted to go, right? I was interested in the brain and really wanted to go there. At that time, if you're a washed-up elite athlete, you turn to adventure racing. And so I did a lot of that. Adventure racing is crazy, right? Some of the events I did were like 6 days long. Like the sleep deprivation and stuff was just horrific. But again, what that said to me was, whoa, what is going on to the brain? Like the things you see after 3 days of not sleeping, running through the bush, it's not right. I came back to Canberra. My partner, Mace, was working in Canberra at the time. I think it was late 2008. I moved back. I remember having a conversation with Sandy Daly, who was the head of sports studies here at UC at the time, and just saying, oh, there doesn't happen to be any jobs around, does there? And then she's like, whoa, I got news for you. And the next thing they're advertising, I think that 5 positions or something came out, and there was 5 of us started around about the same time in 2009. Now I love UC, but UC's UC. It has strengths, but it has weaknesses. It's not a G8, right? It's not one of the big sandstone universities that has people endowing. Was it University of Sydney got given $20 million last week, just on a whim from someone, to do some research in the brain and stuff it was too, and I was looking at it going, oh. But UC is quite small and supportive and allows you, I think, probably more than many places, to forge your own path. And so there was a freedom to do whatever I wanted to, really, from a research perspective. And so I went, that's it. I'm finally going to do what I've wanted to do for a very long time, and that was to try and understand the brain better and its interrelationship with physical activity. It wasn't until 2013 that with some of this, I mean, now I look back on it, very rudimentary research that I did with DISA, for those that know the history around here, and we got it published in 2013. Then obviously, you know, everything just snowballs at some point, right? And I was very driven. I was very targeted in a lot of stuff that I did. I had my OSP, my sabbatical, if you like, over in Canada, where I was taught by the gentleman that you can see that I've got my hands around. His name is Professor Patrice Brassard, lives in Quebec City. If you're going to go anywhere in the world, by the way, go to Quebec City. It's a beautiful place. Where we were measuring cerebral blood flow, and he taught me to measure cerebral blood flow. I convinced the university to buy us equipment so that we could measure it here back at UC, and obviously we've done quite a lot of work since. I've tried to bring a group of people together, and obviously I've used and abused students along that journey to create this group where we do more and more research into that space. I think I have a very good record with students, incidentally. They're all employed in either academia or very specialist research-related jobs, so it's not the worst thing to be my student, incidentally. I've had some really good collaborations with people overseas, in particular VUB, so the Free University in Brussels, and Professor Romain Musson, who was mentioned before. And then we got a break in about 2016, I want to say, with some funding that we got from Australian Defence, or the Australian Army was funding it at the time. And we've nurtured that relationship ever since, and we've had ongoing funding that's done a lot of work. Some of you will know I tried to organise an international conference in 2020. We had a lot of really big international speakers. I was so pumped for it. It was going to be a great opportunity. But the obvious happened, and we cancelled the event. But I just want to point out that was not a loss. I mean, it was a loss of sorts. But in building the presenter list that we were going to get, we've built relationships that we've been jumping on ever since. And so the conference didn't happen, and it would have been great. But honestly, we have relationships from people all around the world because of just the act of trying to organise that process in the first place. And I'm really happy now that we've convinced the European College of Sports Science, asked me why I've done it to the European College of Sports Science, to organise a special interest group. And lo and behold, it's called the Active Brain Special Interest Group, which has officially started and will run at the a session at the conference every year, a European conference every year, starting next year in Paris. And of course, it means I have to go to Europe most years. So hopefully it's really obvious, right? I'm interested in exercise and the brain. And if you look at existing literature, I've finished talking about myself. There are positive and small effects, right? People, well, the research in general talks about how when you do exercise, you become better at cognitive tasks, cognitive performance, if you like. That's a pretty small effect. So, you know, it says G equals 0.097. Just take it from me, right? There's a small effect. It's there, but it's not a lot happening. And so I kind of think, well, what do you mean there's not a lot happening? And people do research and they work out then, well, it depends on the duration. And it depends on the intensity. And it depends on the type of cognition, and it depends on the fitness of those people. And to be honest, it probably depends on 100 other different things. And that kind of makes sense, right? Like, I'm sure you've experienced it yourself, because I think about this and go, oh yeah, sometimes I feel I can think better, I think, when I'm exercising, sometimes immediately after, sometimes a little bit after. But sometimes, you know, not so much. And it turns out it's obvious, I guess, when you think about it, but the intensity matters. And when you do really heavy exercise, there's no benefit immediately afterwards, right? Maybe there is after you've recovered, but there isn't immediately when you finish exercising and you've been exercising super hard. So that's what I'm interested in, right? Understanding those relationships of what is it that is impacting what happens. And so over many years, I guess, we've got onto more of this concept of cognitive control. I just want to mention cognitive control because essentially everything is going to relate to this. And cognitive control is basically, you can think of it as your ability to pursue some kind of goal-orientated behaviour. Now that might mean it's a Friday afternoon and you're lying on the couch and you can see the remote control over there and you don't want to watch this channel, but the remote control's over there. There's a goal-orientated behaviour. How much does it mean to you at that point in time relative to how tired you are? And so cognitive control is a concept that you can kind of think about, your ability to harness the attention to really control a behaviour and pursue it. And that might mean you stay away from that chocolate bar that's there because, you've set yourself a rule that you've already eaten as many chocolate bars that you want, etc. But also, I think importantly actually, if we think about the research that we do more broadly, it might even be just about whether or not people engage in physical activity in the first place. And so cognitive control is about your ability to control your attention to something that is important to you, I guess. And so a few years ago, particularly when we've been doing research with the Australian Army, we have thought a lot about this concept. And so this is just a bit of a mind map of some of the factors that we think are probably important. And so I just want to point out a couple of these things as we go along. So there's the external environment. If it's a really hot day, you'll probably get hot and you're less likely to behave in a certain way, right? If there are people watching you, maybe the external environment is a bit different and maybe that will change your motivation because you want to impress those people or something. So the external environment is obviously going to be super important, but it also depends on your internal environment. Like, are you really fit? If you're really fit, you can sweat more and cool down better. If you have certain genes, you can behave in a slightly different way, perhaps. So all those things need to interact together, and you can imagine, right, there's thousands of permutations of what that might look like. But then it also, we think, depends on things like attention, your ability to control that. It depends on things like, I've written up there, neuromodulatory filter, but all I mean, right, is like what hormones are going on in your head at the time? How tired are you, and how has that affected the chemicals that are in your brain at that particular point in time? And all of those are basically going to weigh themselves up, and they're going to go, I don't like this TV channel, but the remote control's over there. How motivated am I for that relative effort at that moment in time? And so that's what we try and portray in very simple terms from a model like that. And so I've kind of talked through a few of those things. So the demands are also about how complex a task might be. Or another way of thinking about how complex a task might be is how much you've practiced it before. Like if you've practiced it like you're Roger Federer, how to do a forehand, you're not thinking about it anymore, right? It is just automated. I've done it 100,000 times this year, probably. I don't know how many times it hits a forehand. But if it's really automatic, then it's going to be easy to do. It doesn't need much cognitive control. You don't need to think about it. It just happens. So practice is super important in these types of settings. So this is what we talk about, and there's heaps of evidence of this where if there's a simple task, it's very hard to disrupt it, right? Distraction doesn't work very well. Whereas if it is a complex task, you can distract people. So these demands matter. It's one of the factors we need to think about. I mentioned neuromodulation, right? So there's chemicals in the brain. So you can think of that more simply as being like arousal levels. Are you up for the challenge? Are you a bit nervous? Are you a bit hyped for it? Or are you on a real bit of a downer and you're not ready, right? Arousal will change the chemicals in the brain. The sleep-wake cycle. Are you tired? Have you been getting proper sleep, etc.? Are you anxious? Are you stressed? Or have you just been doing something for a long time and therefore you're quite tired of doing it? So these types of things affect that neuromodulatory filter, which I think, incidentally, has run out on my kids. Again, because we've done a fair bit of research with the Army, they were interested in certain types of questions, as you can imagine. And so we even look at things like, you know, there are certain types of malnutrition that might happen, which affect the availability of certain nutrients that you have in your body. And one in particular is tryptophan. Tryptophan is required to make dopamine. And you probably don't know what dopamine is, but I'm sure you've heard the term, right? It's one of those chemicals in the brain which is going to help you do what you want to do and make you feel better when you achieve something at the end. And obviously there are things like a lack of sleep or mental fatigue also lead to accumulation of other molecules, adenosine in this case, which will degrade performance that happens. A few years ago, to be honest, this is an opinion piece, right? This is an opinion article that we wrote. Christy Martin, one of my PhD students at the time, was the lead author on it, where, you know, we just talked about, well, what is mental fatigue and how might it fit into that model that I was showing you before. And the idea, again, is that there are chemical changes in the brain that make sense that would lead to changes in how hard something feels to do. It would make changes to your motivation to do those things in the first place. And obviously the culmination of those two things is that your performance decreases under mental fatigue. And so this was one of the earlier papers talking about, well, what happens in this scenario, this effort-reward scenario, that we could not just think about from a psychological perspective, but can we actually start thinking about what are the chemical changes that are happening in the brain that might lead to lower motivation. It turns out to, you know, like, I just like pointing this out because I just think this is really cool research. Imaging research, fairly recently, has shown the parts of the brain that are generally related to whether or not something feels hard and how motivation and effort is influencing the brain. And so there are central structures in the brain that may not be causing or making these decisions, but are clearly linked and involved in it. So as obviously science and neuroscience in particular keeps evolving, we get to understand more and more about how the brain is working. Okay, so my point is, I guess, let me check my time. The brain is complex, and cognitive performance and the relationship between physical activity is super important. And I think we need to understand that before we can start asking the next question about what is the ideal way of thinking about physical activity from a cognitive health perspective. Because we're not getting any younger, and we know that regardless of any disease states, cognitive performance decreases with age. And there are things you can do to delay or to increase what that curve looks like, but almost no matter what type of cognitive performance you're thinking about, they all start to decline at some point in life. And this is what it might look like overall for the population, but you know, anyone's individual curve will look different depending on many factors, including physical activity. And so when I think about cognitive health and physical activity, I really am thinking about, well, how can we limit damage to the brain? Because physical activity is clearly good for physical health, and physical health is obviously going to be important for the brain. But also, what can we do to optimise the brain in the first place, so that when we do decline, we're still performing at a reasonable level before it ends. Now, physical activity is really well known, obviously, to link into a whole bunch of damage factors, if you like, right? So, you know, cardiovascular disease, high blood pressure, diabetes, weight, All sorts of lifestyle factors are associated with poorer health outcomes, which are also linked to cognitive health over time. But the other way to think about it too is, well, what can we do to increase that cognitive reserve? And obviously you have to do learning, right? There's nothing about physical activity per se that is going to make you think better. It might make you move better, but unless there's an extra purpose, so whether that be wayfinding or doing some other cognitive task at the time, there's nothing about physical activity per se that makes you cognitively better. So what is it that makes you cognitively better? Well, obviously it's just about learning, right? I mean, there's childhood development, you know, the marshmallow test, right? I mean, how do they get better at the marshmallow test and being able to hold back? It's cognitive control, by the way. Being able to not take that marshmallow and wait for a few minutes before more marshmallows come. It's the test they do with 5-year-olds, I think it is. So that's about a learnt experience, right? Where you learn over time that, you know, if you wait, you'll get more. And so you get better at doing that. We go to school, right? So learning works. You learn more things. And not surprisingly, really, if you do cognitive training, then you tend to get better at that type of cognitive activity that you've been training over time. Now that can be with certain computer games, but it could also be with, you know, doing Sudokus on the weekend or whatever it might be. And what is it about that learning? What happens in the brain? And really all that's happening in the brain is that you're strengthening those processes in the brain that allow you to do that. And you strengthen those processes in the brain, those neural connections, through a whole bunch of ways. You can produce more nerves. You can make the nerves have more branches and link to different nerves that are more important for a particular task. You can have just a richer blood supply coming into that area, allowing that nerve to work better for longer because it's got more fresh blood and, you know, toxins and stuff getting flushed away. And you can also do things like synaptogenesis. In other words, just getting the two nerves talking to each other in a much better way, or a much stronger way is how I should talk about it. So synaptogenesis is really, or the synapse, two nerves talking to each other, is done through a chemical process. And we know that when you learn, you basically change the strength that those two nerves can talk to each other. And if they have a stronger connection, it's easier for you to do in the future. Now, of course, to do any type of activity, it's not two nerves talking to each other. It's, you know, a few thousand, tens of thousands. It's mind-boggling. Like, I can't get my head around it, right? But this process, if this happens across the brain in different parts of the body, then wonderful. You learn something, you get stronger at it, you get better at perhaps that cognitive control that goes on. And it turns out that there are certain molecules and certain chemicals in the brain that allow those things to happen. And one of those that is really important is this molecule that you can see in the middle, and that's apparently a picture of it, is BDNF, brain-derived neurotrophic factor. And if we think about BDNF, you can see in the aging brain is related to, you know, the growth of more nerves, better connections between those nerves, the synapses, and also more dendritic branches, better branching between the parts of the brains that matter. And as it happens, the type of work that we do in our lab is we look at, well, what is it about physical activity where we get things about more BDNF? And it turns out you get the most BDNF, we think, when you have the highest blood flow in your brain. Now, the highest blood flow in your brain doesn't happen at the highest exercise intensity. It happens at that point where you just start puffing. You know, when you exercise and you breathe heavier and heavier and heavier, and then you finally get to a point where you can't talk to the person next to you anymore. So sports scientists will refer to that as the lactate threshold, right? Or a ventilatory threshold, right? It's the puff test. Once you're puffing and you can't talk to the person next to you, then you're basically dipping on that top left figure there. And so just before that point in time is where cerebral blood flow, the blood flow to your brain, seems to be the most. And so then we think about, okay, so that tells us something about the intensity of physical activity. Now, we generally think of that as being, for some people it might be a fast walk, or for some people it might be a slow run or a faster run if you're an athlete or whatever it is. But it's a moderate-based intensity, which is dependent for that person. You can achieve it however you want. We often get worried about aerobic exercise versus resistance training. It doesn't matter, right? The intensity is the important one. And when you hit that, then we think there's the most BDNF. And so the type of thing that we think about is, well, let's make use of that. Because if that BDNF and other factors are really important for supporting the cognitive changes or the brain changes that you need to build a healthier brain, then why don't we do both of them together? And that's when we start thinking about doing physical activity and cognitive activity, both at the right intensity, if you like, at the same time to take advantage of those properties. Of course, we also do other work where we think about, well, it depends on where the blood is flowing in the brain, because the blood probably flows to different places depending on what you're doing. So remember right at the start I talked about how when you're doing exercise you have this motor cortex, this strip of nerves from ear to ear. So when you just exercise and don't really think about anything else, blood flow to that part of the brain increases dramatically. That's the medial part of the brain, right? It's supplied by the middle cerebral artery. Very creative with our naming, obviously. When you think, or most of our thinking, most of our higher order cognitive control type activities, we think is highly controlled by the front part of the brain. And so then we start thinking about, well, can we manipulate where the blood is flowing in the brain? And so some of you may have been involved in some of the research that we do in our lab. These are slides from Vicky, where we're measuring blood flow in the brain because of the techniques we learned from an OSP in Canada many years ago. And so we get people to do physical activity and computer tasks at the same time, and then we basically look to see where the blood is flowing in the brain using some ultrasound Doppler. Now, of course, it would be nicer if we could do it in one of those big, expensive magnets. A, we don't have one. Hints, anyone? B, you can't really do this type of exercise in a magnet. So the magnets are quite limiting in a way in that we can't really look at the type of exercise intensity that we think is important. And so when we think about, well, we want to optimize the physical activity to take advantage of these, rich nutrients for the brain and do it at the same time as the cognitive activity, it turns out that there is some evidence, this is pretty early evidence, that this is probably going to be more effective for improving brain health in the long term. So some of the work that we're doing in the lab at the moment, we have one project funded by Defence, where we're basically looking at doing physical activity and cognitive training together. We compare that with just physical activity alone, if you like, or doing the physical and the cognitive activity separately. We have another study we're about to start with our colleagues down the road at ANU, doing the same type of thing in older adults. And we have a new project which will start next year, basically funded by World Cancer Foundation as well as Cancer Australia, where we'll do the same but within a prostate cancer group. And obviously we have a whole bunch of in-house studies where we're really trying to look at the mechanisms that we think are behind these, because we think it's important to understand exactly what's going on. And so we can kind of, I think of it as being, well, if this works, right, then we can start to tailor how we design those exercise programs, or how we design those cognitive programs, depending on the outcome that we want. Do we want, a cognitive performance outcome, just pure and simple? Do we want to know if cognitive control can be maintained for a long time, like that stability question? And that's important in many occupational settings. Obviously defence is going to be one of them with the army, etc. And can we just get better at making an athlete grittier, because we're asking them to do hard physical activity and a hard cognitive thing at the same time? And so depending on what we want to ask or what question we're asking, we're thinking about how we can slightly tweak the design of this concept. And so the concept looks something like this at the moment. Now, this is a fairly limited in a sense, in that it's getting someone to ride on a bike. We control the intensity very carefully, and then we get them to do a cognitive activity on the screen. But obviously with technology changes, maybe there's an augmented reality solution that we can come up with. Maybe there's VR solutions we can come up with in the future. And depending on what our audience is, we can make better brains by basically just optimizing what the human was already made to do. What I mean by that cognitive training, right, is that we at the moment are using a platform. It's an online platform. Anyone can sign up to it. If I haven't convinced you already, I'm not a shareholder in Brain HQ at all, promise. But they basically have a suite of programs or tasks, if you like, where depending on the cognitive aspect that we're trying to change, we can basically try and tailor different cognitive programs to go with the physical training that we're doing. So what are the future studies? I think it's about altering that protocol depending on what we're trying to look at, and I think there is an opportunity here to look at mental health type aspects. There's occupational performance, and obviously there's very obvious healthy ageing applications as well. And so to me, understanding what is lying behind these changes is really important, because that will enable us to better tailor our options into the future. So I'm sure you want to know, what are my current recommendations for a healthy brain? And well, it's probably any physical activity that's going to address any disease type issues or lifestyle comorbidities that might exist. Any physical activity that reduces, sedentary time or increases socialization, anything, because we probably don't give it enough credit, but socialization is cognitively engaging. So we need to think about that as a particular option out there. And maybe there are specific exercise prescription options. Of course, I'm biased, and I'm going to say, well, orienteering is clearly a wonderful exercise prescription. But clearly, there are many other options and the types of things that we're working on that could be facilitated into even just normal gym environments, etc. Thanks for listening.
riding their bicycles. Can I have some questions from the audience? Maybe we've got some really, really hard questions from our littlest people.
I'd like to make a comment.
Question?
I was a Fed orienteer once, but the time I'm referring to was when I was also a part-time computer programmer, and that can be very challenging. I used to do it at home. I'd start at 10 at night. At 2 o'clock in the morning I couldn't solve a coding problem, and I'd be going to bed almost like I was drunk, even though I had no alcohol at all. The next morning I'd go up for a slow run, about 6k, and I'll tell you what, time after time, the problem was solved. It was just a slow run that solved the problem, and that couldn't have been coincidence.
Would you like to comment, Ben?
I think I've got this mic on still. Thanks, Nev. So Nev was working at Actors and was our high performance manager when I first came to Canberra years ago. So Nev's obviously had a very big influence on me. Yeah, look, I just think you're probably taking advantage of mechanisms that are at play that we didn't really understand back then and still don't understand, but I think you're spot on. You're taking advantage of stuff that's happening in the body already. Yeah.
Thanks very much. Professor Janberg.
Can I ask you a totally naive question as somebody who doesn't do exercise, think about exercise? For hundreds of years, poets, other writers, but poets especially, those of us who work entirely in abstract, non-tangible objects, have known that walking, not running, not orienteering, but walking solves problems with poetry and writing. And I can't help thinking that in our lazy, drunken, drug-induced, abstract ways, maybe poets over hundreds of years have picked up something here. We aren't getting rush of the blood to the brain because we aren't puffing, but we are walking and walking and walking, and in the walking, the words fall together.
Yeah, look, I think to me walking helps. It's doing exactly what I was talking about. It maybe hasn't, in this day and age of the modern science, optimised the effect, but I think exactly what you're saying is taking advantage of what I was talking about too. And I think there's a quote by Socrates or something, I think it is as well, who talks about the healthy body and mind as being, and so I think, there's always been this kind of understanding that these things are important and related, but I think we're just getting to the point where we are just, putting our finger on exactly a chemical that's changing that explains what we've kind of suspected for a long time.
So he started running because of poetry.
Maybe you finish verses quicker or something, I'm not sure.
Poets are so sedentary and drink so much, you do get puffed walking. So, that might explain it. But Ben, I was wondering, has your research shown, looking into, the sort of, and I know nothing about any of this stuff either, but looking at brief, high intensity exercise, like, do you just need a rush of blood to the brain briefly and it maintains, or like I would imagine with orienteering, aren't you staying puffed? Like, what? Yeah, and do you just need some short hits and it's maintained, or do you need to, how long do you need to prolong it?
So I remember years ago, this is going to sound a bit lame, but there was a journal called the Scientific Journal of Orienteering, and there was a very, very highly ranked Finnish orienteer that used to, he was obviously a bit over the top, and he used to record and make notes on every little mistake he made and stuff like that. And orienteers get very good at talking about where they lose 30 seconds because they went the wrong side of a rock and stuff, right? Like that's the level that we are talking about here. And he used to link it back to the heart rate traces he did. And he, more often than not, in his papers and stuff, he used to talk about how he was making errors when his heart rate would go over a certain level. Now, it turns out that we've mucked around with this a little bit and done some high intensity stuff and looked to see what happens to cerebral blood flow, let alone all the other things that are going on, because remember, it's complex. And cerebral blood flow doesn't kind of do what you think in high intensity stuff. It actually goes up early, like when you do one thing, but then it starts dropping dramatically. And so, you know, anecdotally, a lot of people will talk about how, I use orienteering, right, but you can think of it in any setting, is when you do something that's really high intensity, you know, it's hard to think for a little bit until you recover. And I struggle to think how that's not related to cerebral blood flow at some level. And so the idea of high intensity interval training is much more complex than even we first imagined it was. It does seem to affect a lot of things a lot more. So I don't know, but I'm not convinced that high intensity stuff is really the way to go. But also, like running at a moderate intensity for an hour is, if you're just after cognitive brain health, that's not what you would do either. Like it's probably something around 20 minutes or something. Like I'm not sure, but that's kind of how we're thinking. We need to understand more stuff so we can get better at being prescriptive about what is an ideal dose.
Thanks, Ben. In my work as a yoga teacher, the physical intensity is much less. My clients are generally older adults like me, and the speed and intensity of our physical work is not very high. However, I like to introduce unexpected, unpredictable sort of movements, or have people focus internally with that interoception. Would those sort of activities qualify as cognitive tasks? Or is that way too low to get the sort of benefit that we would like to think we're getting?
So I'll answer a bunch of those things. I think too often we think about exercise intensity based on comparing ourselves to an Olympic athlete. And because we don't move as fast as an Olympic athlete, we think of the intensity as being low. But that's not what it is. The intensity is important relative to that person's capability. And that's what's going to influence things like cerebral blood flow. And look, cerebral blood flow is not the only thing that we need to think about. So, you know, like I do Pilates classes and stuff as well. And to me, you know, sometimes just holding a position, I'm sure that's getting my cerebral blood flow up, and I'm not really moving. So that's why I think, you know, sometimes we focus too much on it's got to be aerobic exercise and it's got to be a certain speed. To me, it's about being active and getting the body engaged so that it will change cerebral blood flow, because cerebral blood flow is actually most responsive to carbon dioxide levels, and not the speed of what you do. It's the carbon dioxide levels that are in your blood. And so that depends on muscle contractions and a whole bunch of stuff that's going on. We have some interoception researchers in the room here, so I won't go too far there. But to me, no, that's cognitively engaging. But you know, I guess I don't think you can expect, you know, if you're doing unexpected movements and stuff or interoceptive work to improve verbal memory, but you are going to be improving some cognitive processes in the brain. Just exactly what they are, it's hard to know. And I think all those, whatever cognitively engaging and throwing different cognitive activities at people is important for overall cognitive health. Yeah, it's just you can't expect if you do this that you're going to get a big result over here. But overall, from a cognitive health perspective, I think, no, there's nothing that's too low dose. In fact, you know, socialisation and stuff is super important for the brain. And, you know, some people don't think of that as being cognitively engaging. But if you really break down the cognitive activities that are going on, you know, your ability to read that person's body language, to bring up some distant memory about an earlier conversation you had with that individual and bring that back into the conversation. There's a lot of cognitive engagement that's going on there, which I don't think we give credit to. I'm not the cognitive expert, but I guess that's how I think about it. So I think any of that cognitive engagement is going to work. And I guess my point is, when you do the physical activity movement at the same time, you just have a boost to the ability to that particular cognitive stimulus to have a bigger effect in the brain.
Couple of quick things, Ben. In the 1979 Australian Orienteer, a Swedish wrote an article about the 78 women's championships, where he noticed that after they'd had a very fast leg, soon afterwards they made a mistake, and he blamed it on lactic acid build-up in the brain, and it took time to dissipate. And the second thing, for 25 years I was a desk jockey in Boundon office, and I used to go for a lunchtime run, and that certainly cleared my brain and made me better for the day. So I think you should add that to your list.
Thanks, Bob. Yeah, look, it's not lactic acid that's causing the issue in the brain. There's probably some kind of metabolic pathways that are related there, but it's certainly not lactic acid. If anything, to be honest, there's evidence to say lactic acid is helping, not taking away. But you know, at the same time that lactic acid might be building up, because you hear sports commentators talking about lactic acid all the time on TV, it's probably associated with other changes that are probably driving reductions in performance. So you know, maybe they happen at the same time, but it's lactic acid is probably not the evil thing that we've made it up to be. Yeah.
Well, thank you very much, everybody, for your questions tonight, and join me in congratulating Professor Ben Rattray.
Thanks.
And please be invited to come and have supper outside.